So good morning, everyone. Actually, good afternoon, everyone. This is E512. CMOS analog IC design. December 21st. Yeah. So we were talking about current source. So Palash, what do you think? Which current source should I, buy when I go to market? What are the specifications I should keep? Zero impedance. Okay. Which impedance? Input, output. Okay. Then. Okay. Srishti. There is no answer. Vishal.
So minimum voltage variation.
Hmm?
Minimum voltage variation.
You mean has to be zero, but is it correct or
That should be
infinity? It has to be infinite, right? So that you can have the current without any deviation with respect to any voltage. So that slope has to be zero, but of course that slope is equal to 1 by resistance, right? So it's going to give me infinite of impedance. So these are the two things very important, along with of course rating has to be known to us. That is also the thing. But these two are the main specs of any current source. Same way, can you tell me what should be the specifications for voltage sources? Okay, very good. What else? Right? There should not be any deviation because of the current. Yeah. So we are talking about this, and this is very important topic in terms of one thing. Current is required everywhere. Wherever circuit is there, you require specific current which is biased through a circuit. Right? We'll learn about it when we are going to talk about the differential circuit, but this is very important to get the control of the circuit using current. If you don't do that, there are lots of things can happen. So in detail things we will talk when we will have the bigger circuit. However, current is very important, and replicating we are making one master current, actually master current source somewhere, and we replicate from here at many places which are slaves, right? So I should not say slaves, but yeah, I'm replicating the current, right? So if master current I made something like, let's say, 10 micro, I can make multiple of that, like either 20, 10 also, 40, 30, so on and so forth. And same way, 5 micro, 2.5 micro, those are also possible if you wish to do that, right? So this is very much needed for one reason, that we want to make everything PVT independent, right? It has to be PVT independent, and to make everything PVT independent, we learn that things has to be matched, or has to be matched in matching mode, right? So if it is green color, right? But everything has to be same thing, right? So matching is very important in transistor. So how to match transistors? So there is few things we need to understand when you go to any transistor property. You're going to see one of the thing is width. Width is no problem, right? You know what is width. You also know what is length. In general, in digital circuits, people do not touch length. They do not touch length. Even they do not touch width also most of the time. However, sometimes when they make there are two kinds of design: fully custom IC design and one is semi-custom IC design. So the course which you are studying, maybe digital MOS LSI circuits, that's a semi-custom IC design actually. So it requires usage of changing width, length, and all these things. So in that case, you change it, but preferably you do not change length, just to make sure that you can achieve the required bandwidth. If you increase length, there are possibility that the bandwidth or the frequency operation will be reduced, right? So that's why we do not do that. However, in our case, when it's analog, we need to touch length also sometimes, okay, if it is required. So you have to take the decision very wisely, right? Whether I need to change it or not. But other than that, there are few more parameters which are very important, which are going to be useful in the matching of the transistor. So one is called multiplier. So if I am writing something like this, what is the meaning of that? Just you have to tell me. If it is 1 micrometer by 180 nanometer and multiplier is 3, then what is the meaning of this? What do you think? Hmm? Split into 3 means
by lengthwise,
lengthwise.
because the length is larger.
Okay.
So we will split it.
I think so, widthwise.
Widthwise. Okay. One is widthwise, one is lengthwise. You are dividing. You are saying. Okay. Vishal. Anybody else? Kalash. That was one guy last time he was sitting here. What's your name?
So,
Gaurav. Yeah, Gaurav. Any guess?
So the division of gate.
Okay, so whenever look, multiplier name itself suggests that there are 3 transistors which is having width and length of 180 nanometer. The meaning of that is as follows. So if I am doing this for, let's say, NMOS, then this is the meaning of this. When we are writing that, each one of them is 1 micro by 180 nano, each one of them, right? So what is the effective width in this case? 3 W by L. Okay, maybe more things we'll study later on in slides. However, so this is 3 W by L, right? Why we are doing this? I could have written 3 micrometer by 180 nanometer. I could have done that, right? But instead of this, I am doing this. Why to do this? It is all about the matching. Matching means I am making the circuit where the unit transistor size, understand this, unit transistor size I fix to some value. Let's assume that I am taking that value as 1 micrometer by 180 nanometer. These are not the absolute number. Understand, these numbers may vary as per your requirement in terms of GM, RO, and all these things. Let's assume that I fix the unit transistor size as 1 micro by 180 nanometer. Then if I need somewhere 3 W by L, then I am not going to keep 3 micrometer by 180 nanometer, but I am going to keep here multiplier as 1 and other side multiplier as 3. So whatever I am writing here, so this is a technical way to write it down. So generally it's written in papers, not in books. They do not write like this, but in papers they are writing like this. So if it is 1, 3, 4, 5, those are the multiplier. Now what's going to happen if you look at this? Is actually a good idea to make the matching, because if you look at this, so this is the transistor, right? 1 micrometer by this is 1 micrometer, by 180 nanometer. So you know that of course this will not be 180 nanometer, it will have some changes in that value. Same way other things will also change. Now when we are actually making single transistor like this and making another 3 micro by 180 nanometer, to make something control C control V is easy, replicating same transistor is easy, but making new transistor whose dimensions are 3 micrometer by 180 nanometer, there are chances that there is no ratio relation wise, it may not be 3, the capacitance will change, everything will change. So instead of that, if this is the same thing going other place, then there is no problem. You heard about CNC machine ever? Computer numerically controlled machine, CNC machine. So there is something called, in your cadence also you will see that these kinds of dots are there. Not in schematic, I am saying in layout. Something like this. So what is this? This is known as grid. Every technology has some availability of the minimum grid size. So that has to be seen from DRM. Design rule manual will tell you that what should be the minimum grid size, which you need to change. Understand? Nobody will tell you, or it will not be in default. You have to change it when you are going to make the layout. Otherwise, after making the layout, it's going to give you the error of off-grid error. Okay. And what is the meaning of this means? If I am having the CNC machine and this is at the bigger scale, let's say if I want to, draw something like this. This is not possible, right? To draw like this. Only my machine can go like this. You see? Because it can run only on, this particular tree side. This is known as the Steiner tree, by the way. This is so when it's actually creating anything, it's only like this. There is no orthogonal is possible is there. So there are no possibility to draw like this. Okay, in our chip, I'm saying, and there is only any possibility that you go through this way. So then you cannot have the shape like this. It is like this only, and this is the limitation of particular technology, that it can create available metals and other things like this only. So that's why when you want to make 1 micrometer and 3 micrometer, it might happen that because of the technology limitation, those ratio may not be same. It will be different. But I want exact ratio, right? So having the matching and having the ratio will guarantee that things are going properly. What I mean to say, if you remember, if I need some voltage, I use this particular technique, right? I take R1 and R2 in ratio. Ratio will give me the value of voltage, and the value of voltage does not depend on value of the resistances. Actually, if you are taking in the ratio of kilo ohm, mega ohm, giga ohm, or ohms, depending on what you want to drive. But these values are not so much important, but their ratio is more important, right? So we want exact ratio. So you have to keep the things in ratio and to achieve the PVT independent output. So even if I know that resistance may change with some delta R1, right? It can change, right? With respect to temperature. So it can change. But if there is ratio, temperature is independent, right? If this resistance is like instead of 100 kilo, if they made it 99 kilo, and this is just multiply by 3, let's say, and it's a ratio of 3. Ratio does not change, but make sure that the unit size is exactly same, right? So definitely you need to keep 3 resistances in series, then maybe equal size, or So there are many things you can do it. So ratio is the important part. Let's keep this in your mind. And this is called multiplier. This is one way. All company people, they like multiplier. They do not use anything else. But other people who are very poor, and they do not want to waste the money on space, they want to make the tight layout, they use fingers. Finger is a different thing. Now you can guess. Yugal, what do you think? What should be the meaning of finger? Any guess? Wrong guess is also fine. Right?
Grid of the splitting components.
Okay. What do you think? Why I am asking this question to you? That might give the answer.
Because you need to.
Because your previous answer was matching here.
Okay. So that okay. What is it?
So now tell me the answer. What should be the finger?
It was like grid of different splits.
So it's splitting,
Yeah.
right? So both the things, multiplier and fingers, both are actually either multiplying or either dividing. So multiplier is actually multiplying the width. However, finger, if I am writing 3, then there is one more entry, width per finger. So width per finger becomes 1 micrometer by 3, right? So finger comes here. It's division or it's splitting the width. But both has, as I told you, it's this saves area. I'll give you the answer why people don't use fingers in company, because there are certain problems with that also. Like if I'm saying that this is, so this is the top view. So I took something like 1 micrometer by 180 nanometer, multiply by 3. If this was the given property, then I can connect all the gates together, connecting right. Let's make it like this. So this is gate, this is, let's say, source, and this is drain. This is the layout when it's 1 micrometer by 180 nanometer with multiplier of 3, if multiplier of 3 is given. However, in case of W and L and finger is equal to 3, then it becomes like this. So this becomes source, drain, source, and drain. Again, it's gate. You see, it's a compact design generally, right, with fingers. But sometimes it happens that you have to increase the width size or something. Then multiply it better, because you generally make changes in the design if it is not achieving the required results. So that's why it's better to use multiplier, but it's up to you people. If you are very confident, go with the fingers, whatever way you like, right? So this is how the finger based transistor will have this kind of thing. And so if you add all of them, you should have the size of 1 micrometer. Look at this. This is width and this is length, right? So all three width added, then it will give you 1 micro. So it's division. and in this case it's multiplication. Okay. Okay. Is there any problem by the way in width and multiplier and fingers? Okay. I would recommend use multipliers whenever you are going to make the current meter circuit or the next laboratory. Please use multipliers only. Now, if I need to have the current generation, I may have some analog system which is giving me the required current. Let's call this one ID1 because it's flowing through the drain of M1 transistor. This is an NMOS, right? And this one body is connected to this ground. And there is a V bias voltage. If you remember, we used to call this kind of setup as current as a load. If you remember, we did this, right? Either this way or this way. And we never defined what is V bias, right? But you must have studied somewhere. Let's go how V bias has to be created first of all. Let's say in this V bias I can create by ratioed resistances, and other side this is acting as a V bias. Note that V bias is a DC value, it's not an AC value, right? That's why VDD is getting divided through these two ratioed resistances, and VB is given over here. VB is nothing but VB is equal to VDD times R2 by R1 plus R2, right? So that voltage is here. So the tuning either of the resistance or both the resistance, whatever way you like, you can achieve the required value of the VB, and that is going to give you I out, because I out is depending on gate to source potential here. Rest of the things are almost same. So VB is actually tuning the required current, right? Anyway, so this is simple, I believe. Any doubt in this? Now let's assume that this same circuit is actually connected over here, and whatever analog system, I'm writing analog system, but whatever you want to keep it as a load, it doesn't matter, whatever you keep it as a load, the ID1 ID2 are depending on VB. Agree with this one? And another thing is W by L, of course. Right? So if this system is like this, let's assume that if this is W by L times 2, means multiplier is equal to 2, what do you think, what should be the ratio between ID2 by ID1? Right? So double current has to be flowing through this one, and single current has to be flow from this one, and that current is depending on this gate voltage and of course W by L. But if you take the ratio, it gives you the required current, right? Now we already talked about it. What are the main specifications of any current source? Those are output impedance has to be infinite and minimum loss at VDS voltage or minimum voltage, right? I call it VDS because that is what's going to happen in our transistor. Now what I am following is not Razavi. Whatever I have taken, it's from Alan Folberg, right? That book is also good. Reza Razavi is also good. There is no problem. It's up to you, whichever book you want to follow, right? It's all about understanding. Okay. So now if we have a circuit like this, understand, now we are making current amplifier. When it's multiplying, sometimes like master current is I, and other current is 2I, 4I. So we want to make current amplifier. So in that case, R in is there and R out is there. Can you comment on R in and R out in current amplifier? Whose input is current, output is current. Means it's a current control current source. what do you think? What should be the input impedance and what should be the output impedance in your opinion? Low, right? We understand why it requires. This is same logic which we are used to use, or it is same thing in terms of I versus Vi and V out versus IO, right? So because we don't want to change the voltage over here, it has to be same, right? So that is the logic for getting this input impedance and output impedance. This has been given in many books, like including if you go to the Millman Halkias or maybe Sedra Smith, many books are there, right? So this proof is already given. So these are the things, and for a current source, output impedance has to be infinity, and V minimum has to be 0. I am emphasizing on this because I do not worry about input side. I do not give input. I am just going to take the output from there, right? Okay. And what exactly I am going to follow? I am going to make one master reference generator somewhere, and using that reference generator, I am going to generate many current sources from there. If this is IREF, if I want, it's a 2 IREF, 3 IREF, 4 IREF, so on and so forth. You can design, right? Divide also you can do that, right? So this is the main idea, and this is what we are going to do it with single agenda. My output has to be PVT independent, and for that I have to match. First thing is current, right? Many other things we are going to match in you know uh, in our circuits, but first thing which we are matching is current. Sometimes voltage, sometimes many other things are there, right? So sometimes GM, right? But first thing, when it's current is matching, so for current matching, two things are required. What are two things? Output impedance has to be infinite and output voltage has to be 0 as minimum as possible. These two things are there, and that has to be evaluated, right? So let's start with the very simple current mirror which I want to replicate. Let's assume that some current is available with me, I1 from somewhere. Somebody has given me. Let's assume that that's ideal voltage, ideal current. If I do such kind of configuration where this is a diode connected to it, right? Or let's assume that if I am keeping here resistance also, then also this will work, right? VDD minus VDS1 divided by R, that's the I1 flowing through this transconductance. So actual circuit looks like this one. Do you agree with this one? I'm drawing just left part. One side is resistance, one side is 1 by Gm, and I'm taking the one voltage division, because that is what we did it at beginning also. If you remember that VB was there here. Instead of R2, I just kept one diode connected load or diode connected transistor. So diode connection is very simple like this. Whichever terminal you choose, it's going to see only and only 1 by Gm. Right? Either of the way. If you rotate it also, source is up, then also like anywhere you are keeping it, it's going to be 1 by Gm, right? Okay. Okay, if this is the case, I fix the current, right? This side, current flowing through this one, I1 is fixed. Okay. One more thing, okay, this is, I'm telling many times in many courses, unwritten in many books. Some people are saying that also, some papers are also writing, but people learn it through experience. And I'm giving you that experience to you people. So do not forget that to make any good analog circuit, in analog circuit, you have to make sure that VDS has to be more than 250 millivolts, something 250 millivolt or 300 millivolt. If you can achieve this one, look, these numbers are working till whatever technology I work, 28 nanometer or even below that. So this works. if you can achieve VDS equal to 250 to 300 millivolt from a single transistor, means it is like this. If this value, if you are saying 300 millivolt, you are in a safer zone of the transistor which is of saturation mode of operation. If this is what you achieve, there is no need to check. Generally it will give you that this transistor is in saturation only, with the fact that VGS minus VTH and VDS value that you need to see. So I am replacing this value as VDS set. When VDS set value is achieving more than 250 millivolts, there is no problem. You are in the safer zone. Of course, little bit like 200, 250 might give you sub threshold. Many things are there. Depending on your requirement, sometimes you have to deal with it, but keep this in your mind and lock it forever. Do not forget. If you want to become, or if you want to pursue analog as your, domain of expertise after this, right? So let's assume that VDS I am talking about, one transistor, this VDS2 is going to be more than 250 millivolt. This of course has to be up. This value depends on these ratios, right? Okay. So now I know that the current is very simple. I is equal to mu n C ox by 2 W by L VGS minus VTH whole square, right? So if I am looking at output current divided by input current, I can have this equation, and with channel and modulation, this is the equation, right? If both the W by L are exactly identical to each other, if this W by L of one transistor and transistor 2, if they are exactly identical, understand VGS is same, both the VGS are common to both sides, both are exactly same, no problem. If W by L gate and everything is same, body effect is not there or having the same condition, VTH has to be same, right? Can I say this one? Similarly, if I am achieving VDS1 and VDS2 exactly equal, lambda is actually model parameter, mu and Cox are model parameter, so gone. It depends on W by L if VDS1 and VDS2 are not matching, understand, and having some lambda. If they are matching, then this will also go. In ideal condition, without channel and modulation, it is only depending on width and length of both the transistor. And we also agree that why to change length at the beginning? No need to change the length. If it is smallest one, it is only the ratio between two transistors. Or as I told you, if I want to achieve the ratio, I am not going to do like if I want 2I1 over here, I am not going to do 2W by L. I am going to keep this as 2, and I am keeping here means it's a multiplier. Do not touch width. Whatever unit transistor you are choosing, keep it there. This will give you lots of benefit when you are going to make the layout. In layout, there is a guarantee that it's matching and it's seeing the equal capacitances, and this will lead to other things like harmonics and many complex things will come when you are going to design actually bigger circuit like ADC, PLL, SERDES, and many other things. So that's why it has to be matched. Do not forget to match. Now I'm going to tell you one more like important thing. It might happen that if I'm giving you one task to have the current mirror, which is going to give me 20 microampere of current at the output, and I'm going to give you the current of, let's say, 5 microampere, right? This is reference I'm giving you. Let's say I gave you this one here. I gave that, and you found out that W by L, other side W by L of, let's say, 4, right? After doing this, what happened? You are seeing that output is not 20 micro, but it's something like 18 micro. This might happen. Okay, do not change W or do not change L. Tempering with width and length is illegal to get the output when you are going to have the chip, because 18 micro, if it is coming here, it's a guarantee that it will be 18 micro. But if you are doing something W and L here and there, on schematic it's something else, layout something else, and when the chip is coming, it's again something else, right? So it's not PVT independent. So do not touch W and L if it is not as per your expectation. First of all, you have to strictly follow what is there, right? So even if it's something else, because to tune that 18 micro to 20 micro, there are many other ways, but not this way. Okay, so W and L has to be matched. First of all, let's take an oath that we are not going to do any tampering with this and that, right? Because many people are doing it. Even after doing the course, when people are taking tap out and they are showing me, okay, this is the design I made, and to achieve 20 micro, I tune it. So that's why I'm telling you the real life experience. Okay, so this is one thing. Now, the important thing is the sources of errors in the current mirror. The slope in the region, saturation region, is not equal to 0, means you are going to have lambda VDS, 1 plus lambda VDS will be there in your current equation. And there is a channel length modulation. And that means that VDS1 might not be equal to VDS2. So this is very important, that VDS1 is not equal to VDS2 in the presence of channel length modulation. So how to fix it? How to get rid of channel length modulation? If I am asking you how to get rid of channel length modulation.
So we will use long channel devices.
True, right? So you need to use long channel devices, as suggested by who suggested? Who gave this answer? So what's your name? Sumit. So long channel devices may be used. So in that case, it open up one possibility that instead of taking the minimum length, I am going to use 3 times of L. Again, look, there is no proof of such things. We are just telling you some, technique through which all the parametric analysis we did it, and 3L should work. But understand, do this only when it's a current mirror circuit and when there is a problem of channel and modulation, because R0 is depending on by lambda ID, right? So actually ID is affected by R0 and this lambda. That's why we are doing this. In other circuit, do not touch L. Okay, touching L means you are decreasing overall bandwidth. We want very high bandwidth. Some places you might be working on high speed circuits, then that is not a good idea. Do not touch L. But in this case where you require current, and understand one more thing, in this entire circuitry, whatever we are drawing right now, it's a DC biasing circuit. Do you understand what I mean to say here? There is no AC source in entire circuit right now. There is no AC source. This is the supporting circuit to give you the required current at DC, required voltage at DC. So there is no AC thing here which is going to give you, or which is going to deal with the frequency. So on the path of frequency transistors, you are not going to change length, right? So you are going to change the length only when it's a DC biasing circuit, right? Just to get rid of channel length modulation. Means I am going to do this one. This is fine. It's remain same. W by L ratio still remains same. Multiplier is also there. So everything is fine, right? There is no problem. This is what I can do, right? So then if it is 3 times channel length, after 3 times, if you are giving 4, 5, 6, it does not make any difference later on. Of course, there will be some slope will be there. So after achieving so much of slope, there is no possibility to reduce it to 0. There is no possibility, right? So that is the thing, and as I told you, keep it more than 250. It will come automatically, by the way. In this circuit, it will come automatically. In other circuits, you have to work hard, right? But this is the first circuit which we are going to do that. Okay. Are you following till now? Is there any problem? BTech, MTech, PhD, all are here. So, any problem? Or because it's difficult topic, sometimes even though it looks simpler, but when you are implementing, you make mistake. So please do not make mistake. Make 3 times length when it's a current meter. Okay. Now let's go to one extra high level, which is I'm interested in, let's say 10 microampere of reference and 30 or let's say 40 microampere of another current, right? If I want this in reality on layout, how it does look like. So I'm talking about the layout. But before doing this, I believe you little bit knowing about the process step, how transistor is being made. Do you know, right? Little bit. Let's say you are having the P substrate. I'm not going even that first process where how the silica is there and then silicon is being made out of. So those are the chemistry and physics, right? After that, if you have P substrate, you make these kind of big holes. Then you are keeping here n plus. All these things you must have studied somewhere. Right? Then you are keeping other things on top of it. You keep on doing it. But when you are doing this and when you are making the transistor, it looks very beautiful over here. But in reality, as I told you, it does not look like this one. It look like this because it may not be uniform. And when they are creating this, actually they're etching out actually this part through UV, which are at 7-degree angle. So this is the IC fabrication process where they are following why I don't know reason. Okay, why 7-degree? That might be the because of that CNC machine where it's feasible to do that. But there is some angle. It's not exactly perpendicular. It has some angle. If there is an angle, so there are possibility that here might be more slope and here like this, right? So if I am drawing one transistor like this, where this is W by L, and other side if I am saying directly that this is W by L times 4, there is another source of error, which is because of the processing steps, which will not be visible on your cadence ever, because it's under in the process side, in the foundry side. So all schematic designers, they incorporate this error and they try to incorporate this when they are making the layout. So let's go this way. If this is the schematic, one side is W by L and other side is W by L times 4. Every one of us know that 4 means there are identical 4 transistors. We also learn or we understand that if I am going to use, if this is a wire which is connecting from point A to point B, if I am applying here 1 volt, you might think that B might be equal to exactly 1. But there are possibility that in between from here to here there is some IR drop, there are some capacitances, right? So in reality, you might have, it's a transmission line, but it will have so many RC, right? Depending on what is the length, right? And this might not be equal to 1, but it may be approximately 1, right? So this is also going to happen. So easiest way or crude way is, rather than taking output from here, if I am taking from here or taking from here, there are more possibility of having, let's say, B1 point or B2 point having more 1 volt. So take the output from near one. It's another thing which is known to us, right? Means if there is a wire which is connected over here and there are 4 transistors, if 4 transistors are like this, 1, 2, 3, 4, then there are most likely chances that the last 4th transistor will not get the VGS what we wanted to give it to that 4th transistor. This is going to give you an error, or it is a source. It is source of error, so that you will not achieve the required current, right? So what could be the idea? What you can do? So generally, what I keep generally even number of transistors, and I keep this particular transistor. Let's call this one as M1. M1 exactly at the middle, and 4 transistors. I'm doing with the different color so that you can see that. So 2 here and 2 here. I kept it like this so that I can take this. All the gates are shorted, right? All the gates are shorted so that all of them gets equal voltage which is required, right? And whatever is there, like drain to drain, this is source drain, so source drain drain, source drain drain, source drain, right? So this becomes source. In this case, it will go to ground, and drain is the one where, sorry, source is the one where I made a mistake. Let's call this one as source only, but change the name. So all these are the drains. Right? So this is the drain. So this is the terminal over here. Right? Other terminal sources are sorted together. All sources are sorted together. And here, okay, one mistake. M1 transistor is in middle, whose drain is actually giving you I1 current. And this is the one where you are going to get the I0, right? This is how you can make the layout, but still there is a problem. As I told you, because of this 7 degree, look, it's a complete chip together. It's not one transistor made by, made by this robot when it's class 10 facility or whatever way you are making. So it's by robot, but it's not going to make one transistor at a time. It's a billion transistors together. All the layers are getting together. So when it's happening together, this side transistor, if it is 7 degree, just try to visualize in, even though it's in top view, if it is in vertical side or the front view, there are possibility that this side transistor is like this and this transistor is like this, right? There are most likely that all are not matching, even though you thought that this is identical to each other, because this transistor, this side sees one transistor. This guy sees one transistor this side, but this is alone. No one is here. And this guy is alone. There is no one is here. Both are not exactly matching. Means geometrically, if you are saying, they are not exactly same. right? In terms of capacitances, parasitics are not matched. So what is the trick? The trick says that keep same sized transistor over here, same size. Maybe you can keep gate drain all to 0 or wherever you like, so that it can see the same geometry both sides. These are the transistors known as dummy transistors, and these are very important. You have to keep that. Generally, I keep more than two, both side. I keep two to three, like both side. Later on, you can remove some of them. Now, one more important thing is when you are making the layout of current mirror, it is the most important thing that everything should see exactly same thing. So these are seeing same things, but upside and downside might be different thing they're watching, right? This current should not be getting affected by outer side disturbances. So generally, what we do is as follows. We generally keep one big wall of, if it is using NMOS, we are going to keep it here P-tap. P-tap means there are contacts are there. P-type substrate. So white part what you are seeing at the back, it's P-type substrate. If I am connecting such contacts, I can call that one as P-tap coming out, and that P-tap I am connecting to ground, because that is what we wanted to do. So it's got shielded and there is no noise coming from anywhere. If you remember last time we also did that coaxial cable, right? So everywhere we used to keep the ground. Same thing I did with this current, and I take this two connections outside. That's it. It is inside. That is how you have to make a good, current source layout. Is it okay? We'll stop here and we'll study more about current source and mirrors maybe on next section. Are you able to follow, or will you need something to get repeated? Pragya. No, it's not difficult.